Deep beneath your skin, beyond the rippling muscles and the pulsing rivers of blood, lies a framework that silently holds your life together. A structure so refined, so efficient, and so astonishingly strong that even our most advanced engineering marvels pale in comparison. These are your bones, and pound for pound, they are stronger than steel. To call bones mere support structures would be like calling the Great Wall of China just a fence. The human skeleton is a living, regenerating, self-repairing biomechanical wonder, forged through millions of years of evolution and sculpted by the demands of gravity, motion, and survival. When engineers design skyscrapers, aircraft, or space probes, they often seek inspiration from nature's designs, and bones are among the most studied natural materials. Engineers and biologists alike marvel at how a femur, thinner than a broomstick, can bear the impact of running, jumping, and falling. The key to this strength is not merely in the materials bones are made of, but in how they are arranged, renewed, and adapted. The composition of strength. Bone as a composite material. At first glance, bones seem simple, white, rigid, and solid, but under a microscope, they reveal a breathtaking complexity. A bone is not a single substance, but a composite material, a combination of two very different components that work in perfect harmony. The first is collagen, a flexible protein that provides tensile strength, the ability to resist stretching or pulling. The second is hydroxyapatite, a crystalline form of calcium phosphate that gives bones their hardness and compressive strength. Collagen is like the steel rebar inside reinforced concrete, while hydroxyapatite is the concrete itself. Alone, each would be inadequate. Collagen would make bones too soft and bendy, while pure mineral would make them brittle and prone to shattering. But together, they form a hybrid material that is light, resilient, and astonishingly tough. By weight, bone is about 60% mineral, 30% organic matter, mostly collagen, and 10% water. This mixture allows bones to absorb shocks, resist fractures, and even flex under pressure. A cubic inch of bone, roughly the size of a sugar cube, can support nearly 19,000 pounds of pressure, about the weight of 5 pickup trucks. Steel of equal weight would deform under the same stress. What makes this comparison even more remarkable is that bone achieves this feat with biological economy. It's lightweight, self-healing, and constantly rebuilt from within. Steel, by contrast, rusts, fatigues, and requires external maintenance. The microscopic architecture, a living lattice of strength. Zoom in closer and bone's secret comes into focus, its microstructure. Compact bone, also called cortical bone, forms the dense outer shell of most bones. Within it lies a pattern of concentric circles called osteons or Haverian systems. Each osteon is a tiny cylinder of bone tissue arranged around a central canal carrying blood vessels and nerves. This design resembles the rings of a tree trunk, but unlike a tree, these rings are not static. They are constantly replaced as old bone is broken down and new bone is laid down in its place, a process called remodeling. At the microscopic level, osteons give bone a layered, spiral-reinforced structure, much like carbon fiber. Each layer's collagen fibers are oriented in slightly different directions, distributing stress evenly and preventing cracks from spreading. It's a natural version of what engineers call a laminated composite. Inside long bones, like the femur, lies spongy bone, also known as trabecular or cancellous bone. Despite its name, it's not weak or porous like foam. It's a precisely organized honeycomb of thin struts called trabeculae, aligned along the lines of stress. When you walk or jump, these tiny struts bear load like the beams of a suspension bridge. If you could magnify them, you'd see the same geometry that modern architects use in lightweight skyscraper frameworks and aerospace components. This internal scaffolding is a masterpiece of evolutionary design, light where it can be, strong where it must be. The femur, for instance, weighs barely a few hundred grams, yet can bear forces up to 1,800 pounds during a simple act like climbing stairs. Bone, a material that heals and learns. What truly sets bone apart from any human-made material isn't just its strength, its ability to heal itself and adapt to its environment. Break a steel beam and it stays broken until welded. break a bone, and your body rushes to the scene with stem cells and minerals, rebuilding the fracture into something as strong, sometimes stronger, than before. This remarkable property stems from a dynamic equilibrium between two specialized cell types: osteoclasts, which break down old bone, and osteoblasts, which build new bone. These two work in concert like demolition and construction crews on a 24/7 schedule. Every year, your skeleton replaces about 10% of its mass. By the time you reach adulthood, nearly every atom in your bones has been replaced multiple times. But bone isn't just reactive, it's intelligent. Through a process known as Wolff's Law, bones remodel themselves based on the stresses placed upon them. If you lift weights regularly, your bones thicken and strengthen at precisely the regions under the greatest strain. If you spend weeks in space, where gravity is absent, your bones weaken and lose density. They're not just static supports, they're living, responsive machines that learn from the forces they endure. Why bone outperforms steel? By weight. Steel is dense, about 8 grams per cubic centimeter, while bone is only around 2 grams per cubic centimeter. When engineers say bone is stronger by weight, they mean that for the same mass, bone can bear more load before breaking. It's not absolutely stronger. A steel beam of equal size will still outlast a bone, but per kilogram, bone is more efficient. Think of it like comparing a bicycle to a truck. The truck can carry more total weight, but the bicycle achieves remarkable performance with much less material. Bone's lightness gives humans agility and speed without compromising durability. If our skeletons were made of steel, we'd be too heavy to move efficiently, yet no stronger for it. Additionally, bone's hierarchical design, strength at multiple scales, gives it an advantage. From the molecular level, collagen fibers, to the cellular level, osteons, to the macroscopic level, entire bone shape, every layer contributes to resilience. Steel lacks this multi-level organization. It's uniform, which makes it predictable, but also prone to catastrophic failure when cracks begin. Bone, on the other hand, dissipates stress through its structure. Small cracks stop before they grow large, preventing sudden breaks. Evolution